Welcome to a lesson with Dr. Powell. Let's take a look at Dijkstra's algorithm, which finds the shortest path in a weighted graph, undirected graph from a vertex to another one. So how does this work? First, for our starting vertex, we give it a label of 0, and then maybe we have some edges coming out here, and these have different weights. The edges have weights, hence finding a minimal path. So maybe 1, 2, 2, and 3 would be the weights of these coming down. And so what we do is, as we begin, we give a label to all the vertices. The first starting vertex, we give a label of 0, and every other vertex in the graph, we give a label of infinity to begin with. Now, in the first step, what we do is we look at breadth. We look at what's adjacent to V, and we change labels. So it's adjacent, and what we do is we replace infinity by the length of path from that vertex to V. So at least minimally. So we have 1, okay, 2, 2, 3. So we've actually labeled these vertices. Now these are all temporary labels right now, but we make one of them permanent. We make the one that's permanent, that is the least of all of them. So what we've done really is we've actually just taken the permanent label of V, 0, and we've added 1 to it to get this label, 2 to it to get that label, and so forth. So really we're just adding these weights to 0 at this point. And we look at for what's the minimum among these. The minimum among these is 1. So we make this guy permanent, and then we keep on going. And maybe we have like a 5, 4. Here we 5 and 4 right here. And so from a permanent vertex, we now have some adjacencies to make. So we're going to have adjacencies from permanent labels. Okay, so maybe we have 5 and 4 coming from here. Now we go to the next step, and we just simply repeat. What we do is we need to make these temporary. So what are these? We take the permanent label of 1 and we add 5 to it to get 6, and 1 plus 4 would be 5. Now again, these labels are temporary still, but from a permanent label, we're only ever going to be 1 away from a permanent label in our labeling. So temporary labels right here, as we won't become permanent until they become a minimum. So now we look at 6, 5, 2, 2, 3, the temporary labels that are on the edge of where we're searching, and we look for a minimum. Well, we pick one of the minimums. So let's pick this one right here, and we'll make that, and we will make that that guy right there. We'll make it permanent, and then we have maybe 1. And or maybe this edge is 1, and maybe this edge right here is 3. And then we look at this, and we go through the same process again, and then we notice, hey, right, and we label this. So 1 plus 2 would be 3, 3 plus 2 would be 5, and the 6, 5, 3, 5, 2, 2 through 3. We'll notice that the minimum that we get is right here. So that will be permanent, and then we keep on going in this manner. And as soon as we hit the vertex in question and give it a permanent label, we would have solved the minimum path problem. So that's what Dijkstra's algorithm is. Now, its complexity is, at least in this case, is O(n) cubed. That's because at each stage along the way, it's like, okay, so if we have, let's suppose that we have some permanent labels, we're going to be scanning what's adjacent to what's permanent. And so we're going to scan what's adjacent to what's permanent. And when we have to go through all the permanent labels. So if an upper bound for the number of permanent labels is n, And then what's adjacent to those would be n as well. And so really each step you have n squared. If you're going through a total of n things, that's times another n. So this is a crude estimate, yet it does provide an upper bound. And so we have O n cubed as complexity for this algorithm. Thanks for watching.